Many of us have had a urinalysis done for a variety of reasons, and I want to start with the last three things on this table, two of which are subjective or at the opinion of the tester. Urine is yellow, and that comes from a pigment called urochrome. This yellow is created from the breakdown of hemoglobin. Can your urine be other colors? Sure. Should it be other colors? Probably not. Many prescription drugs, many metabolic diseases, they can change the color of your urine and stool. In general, your urine should be on the clear side. Now, that doesn't have anything to do with color, it's just how cloudy. Cloudy urine usually results from the activity of bacteria, but that's not always the only reason. So cloudy urine can suggest a urinary tract infection or a UTI. Leukocyte esterase, it's a product of white blood cells acting on an infection in your urine. And so that value, whether it's positive or negative, can support the visual observation of cloudiness as an indicator of infection. When white blood cells are present in urine, it is called pyuria. I once read somewhere that urine should. Sorry, I can't say this without laughing. I once read somewhere that urine should smell floral. I think I totally disagree with that. Urine has an odor, due mostly to nitrogenous wastes. And however, as urine stands or as it sits somewhere, bacteria like actively start to convert the urea to ammonia. And so it starts to smell like ammonia. I do love what the current book I'm teaching from says. It says that it starts to smell like old diapers. And that is true because the bacteria in the diapers are starting to convert that ammonia. There are a few measurements in a urinalysis that can give you an idea of the level of solutes in your urine. The deeper the yellow, the more solutes. That visual observation can be backed up by two test results, the specific gravity and the osmolarity. Specific gravity is a ratio of the density of your urine to the density of distilled water, right? And your urine has stuff in it, distilled water does not. When urine is very dilute, the specific gravity is low, more like the gravity of distilled water with nothing in it. When the specific gravity is high, there are more solutes present. Osmolarity can also support visual observations about solutes. Osmolarity is the ratio of the amount of solute to the amount of water in the urine. When someone is dehydrated, their urine's osmolarity will be quite high as they're trying to urinate without getting rid of water. This is a great table. At least I think so. This table compares the values of plasma to the values of things in urine. So let's first look at the ions. There's a really wide range of sodium that can be present in urine, 40 to 220 milliequivalents per liter, right? And that big range helps control the tight range of 135 to 145 that's found in plasma. Opposite to sodium is potassium. There is tons of potassium in your urine, right? Your default is to excrete potassium. That's why you need it in your diet, right? And so there's a wide range of potassium that's able to be excreted in urine, also contributing to the tight control of 3.5 to 5 milliequivalents per liter. It's the same for bicarbonate as it is for potassium. There's lots in the plasma, not a lot in the urine. We are always making hydrogen cations all day, and we need that bicarbonate as a buffer. At the bottom of this table are various forms of nitrogenous wastes that can be found in urine. Remember that nitrogenous wastes compare primarily, or I'm sorry, they come from primarily the metabolism of proteins. Look at how high they are in the urine, all of them, compared to the ranges in blood. Urea is astounding at 1,800 milliequivalents per liter compared to the 8 to 25 that can be in your blood. Creatinine is a nitrogenous waste product also, and we can use that for renal clearance as discussed in another mini lecture. Uric acid is the primary contributor of gout or gouty arthritis. In this condition, uric acid is not excreted by the kidney in the amount that it should be, causing a buildup of it. And that buildup happens in articulations, especially those of the lower limbs, such as the knees, ankles, and the knuckle of the big toe. I once saw a commercial for a drug for gout, and it depicted people walking around carrying this big jug of uric acid, and I thought that was a pretty accurate description or depiction of what gout really is. The filtration membrane, or the marriage of those podocytes to the fenestrated capillary of the glomerulus, that prevents red blood cells from escaping into urine. Usually, when there is blood in urine, which is called hematuria, it is fragments of red blood cells rather than full on red blood cells. But you can get full on red blood cells. Hemolytic anemia is an autoimmune function in which red blood cells are prematurely broken down, and they're broken down in circulation instead of in the spleen. And this leaves fragments of the red blood cells in the urine. Your body is waiting for the next famine. No, really. The human race has been subjected to famine for its entire existence on Earth. And you might be like, that's not what it looks like when I go to grocery shopping. There's an abundance of food. Yeah, here, now, but in other parts of the world, famine is a guarantee. That being said, your urine should never contain things that you can convert to ATP. Glucose shouldn't be in there unless you ate an entire cheesecake, and you don't need all of the glucose in the cheesecake. If glucose is present in urine, we call it glycosuria. Lipids shouldn't be in your urine, but lipids are huge. But what ends up in your urine is the breakdown of lipids, the breakdown product called ketone bodies. Ketones are the result of the metabolism of triglycerides. The keto diet focuses on shifting your body's metabolism from carbohydrate seeking to lipid seeking. However, if too many ketones are created, they'll spill over into the urine, creating ketonuria. Fruity breath also accompanies this. Proteins smaller than albumin and some amino acids are also excreted in urine, but at a very low rate. So I want you to take a look at the table here, which compares plasma to urine. Notice how all of the plasma values are above 1, right? They're positive, above 1. All of the urine values, they're also positive, but look, they're all decimals. They're below 1. So these things are largely present in your plasma. I mean, no, pretty much aren't present in your urine. You probably make about 1 to 2 liters of urine a day, so try to think about a liter soda bottle. I read in your book that some medications and diseases, again, I can't say this without laughing, some medications and diseases can make you produce up to 20 liters of urine per day. That's so much. If I took one of those drugs, I would never be able to get through a 50-minute session of class. I'd have to be like, I have to pee, I have to pee, I have to pee. I have been on one of those drugs, hydrochlorothiazide. I had to pee like every 10 minutes. I have some terms here that apply to urine volume. Polyuria is more than 2 liters per day of urine. Oliguria is less than half a liter per day. And anuria is less, or I'm sorry, anuria is none at 400 milliliters per day. So that's a little bit less than half a liter or a little bit less than oliguria. Your body is not ridding itself of the amount of nitrogenous wastes that it needs to. In the case study on renal failure, our patient had oliguria. We were giving our patient water challenges, giving them water, and it was just going to the interstitial fluids in their body, causing more and more edema. If you drink more fluids, or if your blood pressure rises, your urine output will also increase. If you're making angiotensin II, aldosterone, or ADH, your urine volume is going to decrease. Remember, I'm talking about the volume of the urine here, and I'm talking about that not in relationship to concentration or solutes. Those are things that kind of have to consider separately.